If we only see those people who survive, or if we only see a non-representative sample, then we have a bias. And that bias is called sampling bias. The idea of sampling bias is that the sample we observe is not representative of the sample we're interested in. Another way to look at it is the study population is different from the target population. Okay, the target population is the population we're interested in. The study population is where our sample is actually drawn from. And they can be, if they're different, then we have some problem here. Okay? So I'm interested in the entire universe, for example, of funds. But if I only see funds that survive, then they are different. And the difference can be, can lead to bias, and this bias is called sampling bias. Okay? Now, the sampling bias is a general problem. It's not a causal inference problem. It's a general problem. So it's, you have this sampling bias both in statistical or causal inference. If you do statistical learning, if you want to learn the pattern in the target population, but you only see data from a study population that is different, then you're in trouble, right? So sampling bias exists in statistical learning and in causal inference. It's not a causal inference only thing. And one of the important sort of a subset. So one of the important sampling bias is called sample selection bias. A sample selection bias is a special type of sampling bias. Sampling bias just means any time when there's a bias, when the population is different. Okay? The study population is different from the target population. In that case, we have sampling bias. A sample selection bias means what we see is a subset of the large population. Okay? So we're interested in a large population, but we only see a subset of them. In that case, the bias arises is called a sample selection bias. So sample selection bias is about seeing only a subpopulation. So survival bias, we talk about survival bias. Survival bias in the sense that we only see people who survive. Survival bias is a special type of sample selection bias. Right. So previously we talked about self-selection bias. Self-selection bias is about people choosing their own treatment. And because of that, there may be confounding issue. Okay, there's a Z that causes both X and Y. And then in that case, we have self-selection bias. In this case, what we call is sample selection bias, which is we're interested in a large population, but we only see data from a smaller subset of the population. Okay? You can also think about sample selection bias as a missing data problem. You're interested in the large population, but the data is missing. Okay, about the large part of the population is missing because we only see a subset. Right. So sample selection bias. So this will be example, right? So suppose we're interested in the wage or the wage distribution in the entire population, but in reality we only see people who work. So, but we are interested in the distribution of wage if everybody works. Okay. So we're interested in if everybody works, what is the distribution? But in reality, we only see people who actually work. So for people who do not work, we do not see them. So we're interested in this population, but in reality, we only see this population, which is the population that people actually work. Now, how do we go from this to this? Okay? So based on this observed distribution, can I infer the underlying population? Right? Can I? So that is the question here, right? Okay. So dealing with sampling bias. By the way, this is a very good example of sample selection bias, or survival bias, to be more precise. So this is inspirational speaking, right? So we all know what inspirational speaking is. Many people who are successful give speech about how to succeed. Okay, how do you make money? How do you succeed? How to become famous? And they have all kinds of tips. Right? They say you wake up at 5:30 in the morning, and then you pray to God, and you become rich and successful, right? So now sometimes they're not lying. They may be telling the truth. Maybe they do that and they become successful. However, that is typically oftentimes a survival bias or sample selection bias. What do I mean? There are many. So for example, if somebody says, you wake up 5:30 in the morning and do 1 hour exercise, and then you can succeed. Now there will be many people who do that. But many of people who never succeed, and so they never get to speak, right? So this guy succeeds and he speaks. He has the opportunities. So you listen to him, you say, oh, this is the seed of success, but that's purely survival bias, okay? Because you're only seeing the message from people who actually succeed. For many other people who try this, they never succeed, so they never get to speak, so you never see them, right? So this is a typical example of survival bias. And probably the reason why many inspirational speaker, if you follow their message, it never works. Okay. All right. Now, back to our example in our introduction on statistical learning. We have this data set, where we credit card data set, where people's income, people's balance, and we see some people who default, and some people who do not default, right? Okay. So when we were studying statistical learning or statistical modeling, we use this data set to model people's default probability. Okay? Now, the question is, can the relationship we learn from this data set be used to predict default rate for a random credit card applicant? That is the important thing, okay? Because because if I'm a bank and I'm interested in using the available data to assess the default rate of an applicant. Okay, so I receive applications for credit card. So I want to know, okay, is this applicant likely to default or not? So that's the question I'm interested in. Can I use this data to tell me that relationship? All right. So suppose you see a credit card applicant, you see this person's income, and you see how much money the balance this person has kept on other credit cards this person has. So you see the balance information, the income information. Can you predict this person's default rate based on this data? Well, that depends on what this data is composed of. If this data is income, balance, and default status for people who used to have your credit card, okay? If this is your own data from the past about people's default rate and their income and balance if they hold your credit card, then you cannot use this information directly. Why? Because this data is people who have essentially successfully applied for a credit card. So they are survivors, in a sense. Okay? So these are the people who have succeeded in their credit card application, what their default rate is. But you are interested in a random credit card applicant who may not succeed in getting a credit card. So these can be different populations. So you cannot use whatever you learn from this population to predict what happens to random credit card applicants. Right? So this is a typical issue for non-random sampling or sampling bias or sample selection bias. Okay. Right. So how do we deal with it? How do we deal with sample selection bias? In particular, because I'm going to talk in particular about sample selection bias, which is the bias that arises if we only see a subpopulation of a larger population. Okay. So here's the idea. I have a large population. So these are the people who apply randomly, random people. So these are the people who may apply to a credit card, right? But these are the people who actually accept it, right? So these are the people who actually get a credit card. These people who have been rejected in the past. If you only see data from these people who successfully get your credit card, then you're not going to infer the default probability for a random applicant. Because random applicant may well be here. Okay, that's a sample selection issue. Okay? All right, so how do we deal with that? Well, let me use something called C, which is defined a new variable called C, and let me use C belong to 0, 1 to denote whether an individual belongs to a subgroup. Okay, so the setting here is this: I have a large population, but I only see data from a small population. I only see data from this small population, but I'm interested in this large population. I'm going to define a new variable called C, where C equal to 1 here and C equal to 0. Okay. So C indicates whether the individual is observed by me. Okay. C equal to 1 means I see this individual. C equal to 0 means this individual belongs to a population that I do not observe. All right? It's very simple. Okay. Now, I want to know. So suppose my outcome data is y. Okay. So what the variable I'm interested in is y. Y may be default rate or whatever. Okay. So y is what I'm interested in. So I want to know probability of y, distribution y, in this large population. But I only see probability of y conditional on c equal to 1, right? Okay, so that's the fundamental issue here, right? Okay, so I only observe this probability of y conditional on I see the data. But what is the probability of y in the underlying population? Well, there's another way to write it. Okay, which is a bit cute. So the way to write this, there's another way to write it, which is this. The probability of y is actually equal to I can write it as probability of y conditional on do c equal to 1. Can I? Can I do this? Can I do this? So what does do c equal to 1 mean? Yeah. So do c equal to 1 means I make these people be observed. Right? So c means be observed. C equal to 1 means I observe them. C equal to 0 means I do not observe them. So do equal to c equal to 1 means I make these people become observable to me. In the banking example, this means I just give everybody a credit card. Right? I just give everybody a credit card, make them available to me. So that's called do c equal to 1. But if I write it this way, they're equal, right? As you can see, of course, if I make everybody observable to me, then the distribution of y is, of course, the underlying true distribution. Right. So now, what is the problem? The problem is we only see py conditional on c equal to 1. But what we would like to know is py conditional on do c equal to y. So we see this, but we want to know this. Okay? To know this. So how do we do that? Right? So that's a sort of restatement of the problem. How do we do that? Well, if we write the problem this way, as you can see, we're treating this c. C is whether it's observable, right? We're essentially treating the c as our treatment variable, correct? So we can think about the c as our treatment, right? And what I'm doing here is asking the causal effect. Okay, what is the causal effect? What is do c equal to 1? The cause, making everybody observable to me. What is the causal effect on the distribution on y? How do I get this? Let's think about it. Okay, so let's consider this example. Okay, so let's imagine the banking credit card example. So this A is income, this Y is default rate, this C is whether this person actually has a credit card. Now, suppose, so this is a mechanism. Suppose income will cause a person to default. Suppose income is the only factor. Suppose income is the only factor that banks use to decide whether to give somebody a credit card. Because bank can give somebody a credit card based on many, many different factors. Here we are simplifying things. Here we're saying the banks decide whether to give somebody a credit card only based on their income. If income high, I give you a credit card. If income is low, I don't give you a credit card. Suppose. So in that case, A will lead to C, and A will lead to Y. Now let's assume that I do not see the entire population. I only see data from a subpopulation, which is the population that actually gets their credit card. So in other words, what I see is this, okay? I only see the probability of default conditional on people have a credit card. I do not see the probability of default for people who do not have a credit card. Right? In the graph terms, it means that the data we see is conditional on c equal to 1, right? Okay, so, right? Do people see that? So A, because income goes to default, and income will lead to whether a person gets a credit card or not. But we do not see all the people. We only see the data conditional on c equal to 1. This is what we see. So it's we have this conditional here, right? So the data we see is py conditional is equal to 1. Now, how do I get this? How do I get py conditional do c equal to 1? Is there any way to do that? What is the causal effect of C on Y? Remember, if we think about this, the C, whether it's observable or not, or whether in this case whether the person has a credit card or not, if we think about the C as a treatment, right, in the sense that the person who gets the credit card has this treatment of C equal to 1. A person who do not get a credit card has a treatment of C equal to 0. If we think about it as a treatment, then we're asking the causal effect of this treatment on Y, right? So, so the question is, if I simply looking at, so the question is, does this tell me the causal effect? Does py conditional on c equal to 1 tell me the causal effect? Or not? Does it cause, right? Because I see this, right? I actually see this. I do not see this. I see this one. So the first question is, are they equal? Are they equal? If they're equal, how do I judge whether they're equal? Are they equal? Why? Because why are they not equal? According to this causal graph. So this is the correlation, this is the causation. So the question really is the correlation equal to the causation? Is correlation equal to causation according to this graph? Between C and Y? Why not? Because what? What is this? This is a backdoor path from C to Y, right? So the existence of this backdoor path will make, So the existence of this backdoor path will make C and Y correlated even though they have no causal effect. So the correlation is not causation. In other words, this is not equal to this. So how do I get the causation of C on Y? Based on this graph, how do I get causation of C on Y? Condition on what? Exactly, okay? If I condition on A, then I block this backdoor path, right? Then whatever is left between C and Y is the causation, okay? So, very good. So we have our solution. The solution is, what is, okay? So the solution is the probability of Y conditional on do C equal to 1, all right, is the same as the probability of Y conditional on C equal to 1 and the conditional, the probability of P given do C equal to 1, A, P, A, D, A, okay? So we have this relation, and this is, but once we can always write it this way. We just add the conditional A and integrate with A. We can always write it this way. But once we conditional A, the causation become correlation. Correlation become causation. So, okay, once we do that, then this becomes Py given C equal to 1, A. Which means that we simply have Py conditional on C equal to 1, A, P, A, D, A. That's it. And you can estimate this from data, okay? All right, do we see this from data? Yes. What is our data? Our data is everybody who gets a credit card. Do we have this from the data? Yeah, right? Because we can look at people who get a credit card, conditional income, and the default rate. Okay, the default rate conditional on the income among the people who get a credit card. So we see this in the data. We see this in the data. Now, this is a little bit tricky. Okay, we need to know the income distribution among the general population, not just the population who gets the credit card, according to this formula. So if we see PA in the large population, but we see the default rate only among the people who get the credit card, then I'm able to do this, and then I'm able to get the thing I'm interested in. Okay. So that's how we do things. All right. Okay. So I hope. Question?
You mean the A stand for the whole sum?
Yeah, that's right. That's right. So here in order to get this one, in order to get this, I need to know the default probability of people who actually gets the credit card. I don't need to know the default probability of everybody, just the people who get the credit card. But I need to know the income distribution in the whole population, not just the income distribution among the people who get the credit card. Because I'm integrating with respect to PA, which is everybody in the population. Okay. Is this clear? No?
From the derivation process, because it's from the A from the sample I think, so the whole process I think very clear to understand why A changes from the sample to the population.
Well, you can think about, forget about the sample, you can think about the underlying, right? So you can think about, in the whole population, we have this process. Okay? So one way to think about this problem is, forget about what we observe or what we do not observe. In the whole population, right? In the whole population, this is the causal relationship. This is what I'm interested in. Py given do C equal to 1. And I know in order to, in essence, I'm interested in whether there is a causal effect here, okay? So in order to get this causal effect, I need to condition A, right? So this is what we're doing. In the whole population, we can derive this formula. And then based on this formula, I claim that I do not need to observe all the y. Because this formula says I only need to observe y for which C equal to 1. But I do need to see all the PA in the whole population. So we start from the whole population. And then we can derive this formula. And then based on this formula, we know that, hey, I don't need to see all the y. I just need to see y on a subsample. And then I claim, okay, in reality, if you only see a subsample of y, I can actually back out this. You can think about it, okay? Now, this is actually pretty realistic because in reality, banks do have information. In reality, banks do have information about income distribution in the entire population. But oftentimes, they only have default rate for people who actually have a credit card, right? So this is actually a pretty realistic scenario that we're talking about here. It's a realistic strategy, right? So if I only have default rate on people who have a credit card, I can still use this strategy to back out the default rate in the entire population. By what? By conditioning on people's income. So I look at people's income, I look at people who are high income with a default rate, low income with a default rate. And I adjust it based on the distribution of income in the entire population. And I get the average sort of distribution of default rate in the entire population. So that is really the strategy. Okay. By the way, this kind of data where we see all the A, we see A for the entire population, but we only see Y for part of the population, is a kind of censoring data. So you may often hear, people talk about censoring and truncation data. So censoring means we do not observe the entire sample for all the variables. So for some variable, I only see part of the population. I'm interested. For other variable, I see the entire population. That's called censoring. Truncation means for all the variable, I only see a subpopulation. Okay, so truncation has a higher information loss. Truncation is a harder problem to deal with in data analysis. Censoring is a little bit easier. Right? Okay. All right. Let's look at another case, right? So suppose we have this case, right? Let's forget about what each means. I just give you this causal graph. In this causal graph, suppose A is a treatment, and a Y is the outcome, but we only see Y for which C equal to 1. Okay. So that's right. How do we do that? So I'm interested in the causal effect of A on Y. But I do not see. I only observe y conditional on c equal to 1. I do not see y conditional on c equal to 1. So part of y is missing. I see all the a, okay? I see all the a, so this is a censoring case. I see all the a, but only part of y. Right? How do I get py conditional to equal to a? According to this graph. How do we get it? Well, because I only see this. So so what I want to do is I can always write this. I can always write py conditional on do a, given do a. I can always write it as this, okay? As do a and c equal to 1, right? Okay. So I can assume my goal is to what is the treatment effect of a on y if we force everybody to be observed. I can still write it this way. So in this case, we have two treatments. One treatment is A, the other treatment is C. Both are treatment. How do I get it out? From this causal graph. Is this equal to py conditional on A and C equal to 1? Is this equal to this? Are they equal? Because I can get this from data. Because I see all the y for which is equal to 1. But are they equal? Based on this causal graph? Are they equal? Is the correlation between a, c, and a y. Now think about one by one, right? Is the correlation between a and a y conditional on c equal to 1? So conditional on c equal to 1. Is the correlation between A and Y the causation? Are they? No. Okay, right? Now, on the other hand, conditional on A is the correlation between C and Y. So fix this A. Is the correlation between C and Y the causation? Still no. So is there any way to turn this into causation? Should be pretty easy. I just need to, yeah, right? Because the problem here is there is a backdoor from C to Y. Okay, that's the only issue here. So as long as I can block this backdoor, I'm good again. So all I need to do is conditional on L or U. So if we do not observe U but we observe L, suppose U is unobserved, then I just need to condition L. Okay. Right. So again. So py given to A, you can write it as py given to A, also C do C equal to 1. And that is equivalent to py conditional A, L, conditional L, and C equal to 1. Because once you conditional L, you block all the backdoor path. Whatever left is the causal. Okay? And then PLDR. Now, do we see this from the data? Yes. Because I see all the y for which C equal to 1. Do we have this from the data? That depends. Okay, so if you see the L, if you observe the L in the entire population, then we can do this. If you do not observe L for the entire population, then you cannot do this. All right, so in order to do this, we have to be able to see the L for the entire population. That's the requirement. All right, so if you do not do that, then you cannot do it. Okay, you can do it. Okay. So this is our example of how to deal with sample selection bias. So when you deal with sample selection bias, you can think about observability as almost like a treatment. So once you have your causal graph, and you can the mechanism, the way to get the causal effect you're interested in, the way to draw inference about the large population is to think about this C, which is observability, as almost like a treatment, and then try to block all the backdoor path. And whatever you left should tell you about the larger population. So that's a general strategy of dealing with sample selection bias. Okay, you can think about how to apply this to your empirical analysis. All right, so that's it. Okay, so we have talked about. So in summary, all right. So in summary again, we begin by saying, if we observe F and Y for all the population, then in order to get a causal effect, it depends on what else we observe. If we observe W, back door. If we observe E, front door. If neither one, we use C as instrument. Right, so that's our first part. But then if we only observe part of Y, not all the Y, then we can use the strategy I just talked about, treating observability as a treatment, and think about how to block the backdoor path in order to find out the Y in the entire population. Right, so that's really, okay, so that's the logic we have covered so far. Okay. Okay. So far, this is all I want to talk about in terms of causal effect learning, right? So if you remember, this lecture is called the Foundation of Causal Inference, right? So this lecture is called the Foundation of Causal Inference, but causal inference is two things. The way I define it, two things. Number one, so what is causal inference? Causal inference is two things. The first thing is what I call causal effect learning. Okay, so causal effect. The second is causal mechanism. So far, our entire energy has been spent on talking about causal effect learning. So what is causal effect learning? The causal effect learning is I give you a mechanism. I say, look, X, Z, Y, Z cause X, Z cause Y, X may cause Y, right? So how do we estimate the causal effect? Well, we control Z and okay. So this is what? This is I give you this causal mechanism. And based on this causal mechanism, you estimate this causal effect for me, right? So this is causal effect learning based on an assumed mechanism. But where does this mechanism come from? Right? So where do you get this causal mechanism? Okay? So causal effect learning is easy, relatively speaking, because causal effect learning the requirement is we get this causal effect when we already have a mechanism. So we assume a mechanism, and based on our assumed mechanism, let's try to learn this causal effect. This is called a causal effect learning. But causal mechanism learning is harder, because causal mechanism learning, the goal of causal mechanism learning is to learn what this structure looks like, okay? So this is the harder part. The majority of applied econometric research is causal mechanism, not learning mechanism, right? The mechanism is developed by theorists, by economic theorists, by people who do theory, and we develop economic theory about how things are related to each other, what is the mechanism, and based on that understanding, we design strategies to learn the causal effect we're interested in. That is the majority of econometric research. We're not trying to learn this causal mechanism. Okay, so causal mechanism learning is much, much harder. Right? In fact, I would say that this field is almost not developed very much at all. Okay, all right. So now let's think about this question of how to actually learn the causal mechanism. Okay. Now the causal mechanism is typically represented by a causal graph like this, right? So we have once we give a variable A, B, C, I want to know what their relationship is. Does A go to B, B goes to C, A goes to C, or maybe A goes to B, C goes to B, C goes to A? Like, what is it? Okay, what is the relation between them? That's called a causal mechanism learning. Now, in general, right now we do not have an algorithm that can automatically do that. There's no algorithm that can automatically find out the causal relation between the variables. What if we do? What if we have the algorithm that can automatically find out the causal relation between variables? Do you know what that means? Do you know what that means? what if we have an algorithm that can automatically find out the relationship, the causal relation between variables? So that essentially, what if we have an algorithm, a method that can do causal mechanism learning automatically? Then what? Then we don't need any scientists, right? Okay, right? Because quantum mechanics, evolution theory, everything is a causal mechanism, essentially. So right now, the way that we have been doing science is that we have theorists who essentially come up with theories about this mechanism. And then we have applied people, empiricists, who do experiments or look at data to try to really see whether the theory is correct, or to estimate the parameters we're interested in and apply to problems. Now, if we have an algorithm that can automatically do this, then there will be no need for any theorist to design a theory, because essentially it's saying that we can directly find out quantum mechanics by itself. Okay, just let the algorithm do it, and the algorithm will find out maybe something better than quantum mechanics. I don't know, right? So this is far away in the future, right? Because if this can be done, then we have true artificial intelligence. Okay, now because so far what we call artificial intelligence has really no intelligence. Because so far, what we call artificial intelligence is basically finding out patterns in the data, and there's no ability to do causal inference. A true intelligence means you can do causal inference. If the algorithm has no ability to do causal inference, if the only ability is pattern discovery, there will never be true intelligence. The robots will never replace a human. The unique ability of human beings is actually the true mark of intelligence. Is the ability to do causal inference. Is the ability to discover mechanism like this. Okay, so that's the true ability of human intelligence. So one day, right, if the true AI will be an algorithm that can automatically do causal mechanism learning. So far, we're far away, right? But there's some research already. People are doing a subfield in computer science called causal search is really a literature that tries to find out whether we can design how do you design simple mechanisms step by step to try to find out the causal relation. But this is a very, nascent research literature. We're still far away from ever being able to, we still don't know whether we ever can do that. But this is an interesting direction, right? But before, but one question here is this: is it even possible to design an algorithm that automatically discover causal relationships or causal structure? Is it ever possible? In some cases, it may not be possible. Okay? Very simple. If I give you A and B, now, if there's only these two variables, if A and B are the only two variables, can you ever find out whether it's A cause B or B cause A? Suppose these are the two possibilities. Can you ever find out from data? The answer is no. Because the data tells me the joint distribution of P and A, right? And so in other words, the data only tell me that these two variables are correlated. But is the correlation caused by this direction of causation or caused by this direction of causation? You will never be able to know. There's no way for you to tell them apart if you try to find it from observation data. Okay. Now, in graph terms, so in graph theory, we say these two are observationally equivalent graph or equivalent structure, okay? Or graph, causal graph. So these two graphs are observationally equivalent in the sense that they have exactly the same joint distribution, and there's no way to tell them apart. Again, the data only tell us joint distribution, right? And it's really your goal to sort of getting the causation out of it. So these two have exactly the same joint distribution, so there's no way for us to tell them apart. That's called observationally equivalent graph. Okay, so is there any? It turns out that we have a general theorem that can tell us what kind of graph are observationally equivalent. Let's go to. Let me try to. Okay, so let's see. Okay, so we have A goes to C, A goes to B. That's and all right, so, okay. First of all, I would say these two are not observationally equivalent. They are not observationally equivalent. So if they're not observationally equivalent, I can tell them apart. There's a way for me to figure out whether our data has this structure or this structure. If I'm choosing between these two, there's a way for me to find out. How do I find out? Very easy. This graph implies that conditional on A, B and C will be independent, which I can test, right? Which I can test this using data, right? Just fix A and test whether they're independent. And this graph implies that conditional on A, they're still correlated. So I can do a simple conditional independence test to figure out whether this is the true structure or this is the true structure. So this is a general way of finding out. Okay, this is a general way of finding out which structure is true. Okay, so and then in that case you can learn the mechanism. However, like I said, this structure and this structure, these two are completely observationally equivalent. So there's nothing I can do to tell them apart. Right? So that's the idea. Okay. So what kind of structure is observationally equivalent? There's actually a theorem. Okay. The theorem is we first need to define several things. We define a skeleton is once we have a graph and we remove all the arrows, that's called a skeleton. Okay, the skeleton of the graph is removing all the arrows. I'm also going to define something called immorality, so that's a funny concept. An immorality in a DAG, directed a graph, is a configuration of three nodes A, B, C, such that the C is a child of A and B, but A and B is not directly connected. So if we have A, B, C, A goes to C, B goes to C, but there's no connection between A and B, we call this an immorality. Do people know why it's immorality? Because C is the children of A, and C is children of B, and they're not married. So it's immoral, okay? That's called immorality. That's true. That's why it's called immorality, okay? So there's a theorem. It's just called Markov equivalence or observational equivalence. It says two DAG are observationally equivalent in the sense that they represent the same set of independence assumptions. Not just the same joint distribution, but also the same set of independence assumptions, right? Conditional on something, whether they are independent. So they imply the same set of conditional independence assumptions if and only if they have the same skeleton and they have the same set of immoralities. So if two DAG have the same skeleton and the same set of immoralities, you can never tell them apart. There's no way to tell them apart using observational data. Right. Now in that case, right, so this is sorry. So this is an example, okay? Are they observationally equivalent? You can think about it yourself, but in this case, A, B, C are observationally equivalent. They're all observationally equivalent, but this one is different. Maybe you can see immediately why. First of all, these three have the same sort of immorality. So these three have zero immorality. This one has one immorality, right? So they have the same set of immorality, and they have the same set of skeleton. Skeleton means just removing all the arrows. They look like, right? They're the same thing. Okay. So these three are observationally equivalent, meaning that we will never be able to tell them apart. There's no way to tell whether it's this case or this case or this case. But we will be able to tell these two things apart because these two are different. They're observationally different. How do we tell them apart? Very easy. This one implies what? This one implies what? This one implies A and B are correlated or independent? Independent, right? Because this is a collider. So this one, A and B are correlated or independent? Correlated. So simply by testing the correlation between A and B, we can know which one is which one, right? But here, these three, there's no way to tell them apart. This is called observation equivalent. So when we learn causal, so a general principle, right? There's no automatic. Let's go back to that. So when it comes to causal mechanism learning, so far, like I said, there's no general mechanism, there's no general algorithm that can help us do that. But the general principle, right? If we can think about the general principle, how to do this. A general principle is I simply test all the independence assumptions in a graph, and then I can tell, I can figure out which one is which one, right? Is this structure, which one is the true structure? But when it comes to observational equivalent structures, there's no way to tell them apart. In that case, what can you do? You can do an experiment, okay? Because when there's observational equivalent, there's no way to tell them apart from observational data. In that case, the only thing you can do is to do experimentation to find it out, right? So it's very simple. No way to tell them apart. So how do you actually find out whether this is the case or this is the case? You do experiments. You change A, you manipulate A, see whether B changes. If B changes, then we have this direction. If you manipulate B and A changes, then we have this direction. So when it comes to observational equivalent structure, experimentation is the only way to tell them apart, right? So in that case, you can imagine that if we ever have have an intelligent algorithm that can automatically try to search for causal mechanism, you can imagine that this algorithm will be something that would tell, that would use the observational data to try to figure out which is the true structure. And if it cannot figure out, because they're observational equivalent, it will recommend experimentation. Or maybe it's a robot that can conduct experimentation itself, right? So you can imagine a future algorithm like that. But the general principle is, if we have observational data, we can use it to tell apart observational and inequivalent structure. And when they're observational equivalent, then we need to do experimentation to find it out, right? You can even think about science, the traditional role of science, as using experiments to figure out observational equivalent structures. Okay, so that's one way to think about it. Okay. All right. So that's it. Okay, so that's all I want to talk about. So this, we spent about 2 minutes on causal mechanism learning, and that's it. Okay, so we talk about causal effect learning, and then we talk about causal mechanism learning. All right. Before the next topic will be structural estimation, which is the estimation of structural models, theoretical models in economics. But before talking about structural estimation, I want to spend the rest of today's class to talk about traditional econometrics. So let me go back to. Okay, so I want to spend some time talking about the connection between, because the method we've been talking so far is based on causal graph, right? So how to choose variables, what's the strategy, it's based on causal graph. But that's not how you learn econometrics in your introduction class. When you learn econometrics in your introduction class, it's sort of like a different type of criteria. So for the rest of today's class, I was try to spend some time to make the connection. What is the connection between the Bechdel criteria, for example, and the criteria that you learned in your introduction econometrics class? It turns out that they're the same, okay? Now, the Bechdel criteria says if I'm interested in the causal effect of x on y, in order to do that, I need to condition or need to control for variables that can block all the backdoor or open backdoor path. So if there is something like a z that goes to y, okay, I need to control for z because z blocked the backdoor path. Okay. Now, it turns out that let me use this sy. Hold on, let me see. Okay. So let me use the variable v, or maybe maybe v. Okay, just let v. So let me use the variable v to denote all the other causes y. So x can be a cause of y. And let me use the variable v to denote all the other causes y, other than x. Okay? So it turns out that the Bechdel criteria is equivalent. So suppose z satisfies Bechdel criteria. That means conditional on z, all the Bechdel path between x and y is blocked. Okay? In that case, we say z satisfies the Bechdel criteria. Now it turns out that the Bechdel criteria is equivalent to requiring z is independent of x, conditional on, v is independent of x, conditional on z. It is the same requirement. Do people get what I'm saying? So the Bechdel criteria, if z satisfies the Bechdel criteria, then z is any variable that conditional on which all the backdoor is blocked. So there's no backdoor from x to y. Okay? Open backdoor from x to y. Now, the Bechdel criteria is exactly the same requirement as the requirement that this v become independent from this x, conditional on this z. Okay? First of all, why? Why is that true? Well, if I block, if there is a so let's think about it, right? Now, if there is an open backdoor path from x to y, right? There's an open backdoor, and if it's not blocked, then there is a variable somewhere here, right? Let's call this variable s. Okay, so there's a variable s here, and s will cause y, right? Okay. So if there's an open backdoor between x and y, then there must exist a s variable, which s is a cause of y, between which there's an open backdoor from x to s. Do people get it? So if there's open backdoor from x to y, there has to be an open backdoor from x to s, where s is the cause of y. Do people agree with that? Right? Because it's impossible to be any other case, right? So in other words, in that case, x and s will be correlated. So x will not be independent from all the other causes y, because v is all the other causes y, including this s. So in that case, x and s, v will not be independent. Do people follow that? Okay. And no? That's a little bit weird. V means all the other causes y. Okay, all the causes y. So if there's no backdoor between x and y, it's okay. But if there is an open backdoor path, then the open backdoor path has to go through some causes y. Right? Has to go through some causes y. It's impossible, right? It cannot be a direct link like this. It's impossible. It cannot be a direct link like this because we have this circle. It's impossible. So it has to go through some causes y. In that case, x and the v will not be independent, and that will be correlated. Do people follow this argument? Okay. But this is just a requirement in your econometrics textbook, right? When I say x is independent of v, conditional on z is anything satisfying Bechdel criteria. This is exactly the requirement in your econometrics textbook. Why? Remember what is the requirement for causal effect in your? Remember in your econometrics textbook we say okay, y is equal to beta 0 plus beta 1x plus e, right? Plus e. And we say this beta 1 is unbiased if what? What is the requirement for beta 1 to be unbiased? If x and e is what? Independent, right? Uncorrelated, okay? So x is independent of e, right? But what if they're not? Suppose I can control for something, right? Suppose there's a z that I can control. Then I control for beta 2z plus e. Now z is the control I add in, right? So the argument is if I add a control z, E and X become independent. In that case, I can identify the causal effect, right? But what is this E? This E is any cause of Y, right? Other than X. So this E is our V here. Do people see that? This E is exactly a cause of Y that is not X. So the requirement that X and E are independent, conditional on Z, are not correlated, conditional on Z, is exactly the requirement that X and other causes Y are independent, conditional on the Z. So in other words, that's exactly the backdoor criteria. So the backdoor criteria is equivalent to the traditional requirement that this error term is independent, is not correlated with X, conditional on the variable that you control. They're the same requirement. Okay? So hereby I make the connection that essentially the backdoor criteria is the familiar, okay, is the familiar requirement that the error term is incorrelated with your X. Same story here, okay, same story. So why do we go through all the fuss and talk about graph theory? So if the traditional, if the criteria is the same, why do we not just use the whatever that you are talking in econometrics? So that's my next topic, because I'm going to spend the next 20 minutes criticizing traditional econometrics. you may choose to disagree with that, but let's see. Okay. Okay. Well, it turns out that there is a significant. So we understand, right? In the traditional econometrics way of teaching, that the requirement that X and E are uncorrelated is essentially the backdoor requirement. It's essentially the backdoor criteria. But it turns out that the traditional econometric approach has significant limitations, or at least it leads to a lot of confusion. It may be correct, but it leads to a lot of confusion. So first of all, let me just say this. Why in econometrics you are taught that linear regression only work if X and E are uncorrelated? Is that what you're taught? Because when for example, when I read, Watson, Stock Watson's textbook, for example, right, it says the requirement for linear regression is that X and E are uncorrelated, right? But you open any statistics textbook, when you talk about linear regression, you never see that. You only see that in econometrics textbook. Because when you do linear regression, remember when I taught linear regression in the first half of the semester, do we ever say X and E has to be uncorrelated? No. There's nothing. Linear regression is a fitting a line. There's no requirement. Linear regression is simply, I give you some data, and you fit a line to it. There's no requirement about E and X, okay? So anytime I give you some data, you just fit a line. This line is what minimizes the L2 loss function, and that's it. This is the linear regression line. There's no requirement about E whatever. Actually, if you remember my lecture on linear regression, you will know that once you do a linear regression, it's automatic. The E is automatically independent from X. It's automatic. I see you don't remember. So let's see, all right? The question? Okay, so let's see. All right, so once you do linear regression, once you do this beta, you minimize the loss function, right? L2 loss function. Okay, once you find out the optimal beta, you can prove that X and E will always be, uncorrelated, because the mean of E is 0, so it's basically uncorrelated. Okay, so once you do a linear regression, then this E is what is left, right? So beta hat, so Y minus beta hat X, whatever left is this E. This E is always going to be uncorrelated with X. It's never going to be correlated. So why is this a requirement for econometrics textbook? Okay, right? It's true. when you have data and you fit a linear regression line, the error will always be uncorrelated with the x. And also conditional x, right? Because once you give the minimum L2 loss function, if you minimize the minimum L2, the distribution of the error will always be mean zero conditional x, and we uncorrelate with x. Okay? So it's always going to be the case. So why do we even require that in our econometrics test? That's because, okay? That is because. That is because in traditional econometrics textbook, there's a confusion about what is the statistical model and what is the causal model. So in our causal inference, we said the causal inference is two-stage. The first stage is causal reasoning, identification. The second stage, how to turn causal object into a statistical object. The second stage is try to find a statistical model for it, okay? But in your traditional econometrics textbook, the two stage is confused together. Now, in reality, here's what happened, okay? We have a causal model. Now, the traditional way is we have a causal model, which is y is the consequence of x. So y is equal to alpha 0 plus alpha 1 x plus u. Here, x and u are two causes of y. Okay, so y is so it's like x and u leads to y, all right? Okay, leads to y. All right, so maybe there's some relation here too, okay? So this is the causal model. Now, we are interested in this alpha 1 because alpha 1 tells me about the causal effect of x on y. In order to estimate this alpha 1, I can do what? I can run a linear regression, which is a statistical model. When I run the statistical model, there's no requirement about uncorrelated. Well, I do not require this E and beta uncorrelated. There's no such requirement. Because when I run a linear regression model, the E will be uncorrelated with the X whenever you run a linear regression model. However, what I'm interested in is to try to run this linear regression model in order to find out this alpha. So the question is, under what circumstance is this beta 1 equal to this alpha 1? That's the real question. And the solution, the answer is when u and alpha 1, when u and x are uncorrelated, then this beta 1 will be equal to alpha 1. Do people see the logic? Why? Because when u and x are uncorrelated, we satisfy the backdoor criteria. Right? Did you get it? X and u, if x is uncorrelated with any causes y, the backdoor criteria is satisfied. The correlation becomes the causation, and you can immediately use a statistical model to fit it. So that's one reasoning. That's one logic. The other way to think about it is this: when you run the linear regression, the E will always be uncorrelated with X. So the beta 1 will only equal to alpha 1 if the same is true here, if U is uncorrelated with X. If U is correlated with X, then beta 1 will never equal to alpha 1. Because why? Because in this case, E is always uncorrelated with X as a result of linear regression. All right? So here is really what's happening in econometrics, is that we're assuming a causal linear model. We're assuming the causal relation between x and y is linear. And then we say if u and x are uncorrelated, then we can use linear regression statistical model to try to find out the alpha 1. That's the connection. Okay, that's why when we are doing causal inference in econometrics, we require this u and x are uncorrelated. Not because the linear regression itself requires that. Linear regression is a statistical model. It has nothing to do with causal inference. Okay, so linear regression itself doesn't require that. But because we try to use it for causal inference, we require them to be uncorrelated in order for beta 1 to be equal to alpha 1. That is really the story. But this story is quite unfortunate. Why? Because it leads to a lot of confusion, right? The traditional econometric approach does not clearly distinguish between causal reasoning and a statistical modeling. So to me, that is one of the major sort of deficiencies of the traditional econometric approach. In my, when I talk about causal inference, when we talk about causal graph, right? Using a causal graph, it's very clear. Causal inference is two-stage. The first stage is purely reasoning, causal reasoning. How can we transform a causal effect, a causal object, into a statistical object? The second stage is choosing an appropriate statistical model to get that out. So it's very clear what is causal, what is statistical. In the traditional econometric approach, they're sort of they're confused together. This is a causal model, but also we're putting some kind of statistical assumption on it. So at the beginning, even in the very beginning, it's not clear what is causal, what is statistical. Okay, so that is really that's the first criticism. Okay, the second, right? So the real, so it'd be better. It would be better if we can, in fact, if we think about it, we should write 17. If we treat 17 as a causal model, then the better way to write it, instead of writing equal, we actually should write alpha 0 plus alpha 1 x plus u. It's better to write this way because I like to use this notation to mean that this is a causal relation. X and u are causal y, not just equal. And the second equation is a statistical equation, which is basically a linear regression model, which is the equal sign, okay? Because this statistical, there's no causal information. Here we have a causal assumption on it. So the alpha 1 is a causal parameter. Beta 1 is a statistical parameter, right? And all we are saying is when u and x are uncorrelated, then that this statistical parameter is the unbiased estimate of the causal parameter, okay? This is really the logic in this approach, right? So so this is actually taken, I think, from Watson. But when it says the error term is correlated with the regressor, the estimation result is biased. When it says so, the error term is really referring to the u, not the e, in our first equation. And I would think a better way to say it is when the other determinant of y is correlated with x, not the error term. Right? So I think that's a more precise way of saying, because it's a causal model. Okay? And when it says the estimation result is biased, it is saying that our beta hat is not equal to alpha. It's not saying that our beta hat is not equal to beta star, because beta hat will always be an unbiased estimate of beta star. Right? What is beta star? Beta star is simply whatever minimizes this relation in the underlying population. We know that linear regression is unbiased. It's always unbiased. It's unbiased in the sense that beta hat will always be an unbiased estimate of this beta star, which is the beta star that minimizes the L2 loss function in the underlying population. It's always unbiased. But it is biased estimate of alpha, okay, when u and x are correlated. Okay? So that's really, I hope this clears up the logic. Okay. All right. Now, what else? So the requirement that u is linearly uncorrelated with x, is often stated as so really the problem here is most econometric textbooks use one equation to represent both the causal and the statistical model. So confusing what is causal, what is statistical. The requirement that u is uncorrelated with x is often stated as an essential assumption on the linear regression model itself, under which OLS is unbiased. Okay, so this is again, to me, it is confusing what is causal and what is statistical. All right. So here's one example about the need to be careful about causal equation and a statistical equation, about structural causal equation and statistical equation. Like I said, if the equation is causal, I prefer something like this because it tells you clearly what the causal assumption is, right? If you do not make it clear, if you use this equal sign, then it can lead to a lot of confusion. Okay. So for example, suppose let's take this example, right? So x is a uniform 0, 1. Y is a uniform 0, 1. And let me have this causal model, which is u is determined by 1 minus x. Okay? So y and x together determine something called u. Now, if that's the case, what if I estimate a model of y equal to alpha x plus u? What if I estimate this model? Now, does this model actually describe this data? Yes, because the true data in which, the true data has alpha equal to 0, right? Oh, sorry. Alpha equal to 1, right? Alpha equal to 1. Because u actually is 1 minus x. Okay? But what if I run a linear regression on this one? if you, you know, so the message here is this: this equal sign is not a causal relation. I can always write y equal to alpha x plus u. But according to traditional reasoning, if we run a linear regression on this of y as a linear regression of x on u, the alpha estimate will be biased. Because why? Because u and x are correlated. Is u and x correlated? Yes. Okay. So u and x are correlated. So in this case, we say the alpha hat. If we run a regression of this, the alpha hat will be biased because u and x are correlated. However, is it true? Okay, is it true that when we run this linear regression, alpha hat is biased? Is that true? Now it turns out that when you run a regression of y on x and u, okay, the alpha hat you get is not a biased causal effect. It's not a biased causal effect. Right? Because alpha is not the average causal effect of yx, because this is not a true causal model. It's very simple. The true causal model is u as a result of y minus x. The true causal model is not y is an effect of x plus u. This is not a true causal model. So you can estimate this alpha, but it doesn't mean anything. You know what I mean? Okay, so once you're not clear about this, you say, oh, this x and u are correlated. That's why there's endogeneity. That's why this alpha is biased. And this is totally wrong because this is not even a meaningful causal model. So do you understand? Okay. So in other words, this criteria, the criteria that x to u has to be uncorrelated. If they're uncorrelated, this alpha is unbiased. Otherwise, they're biased. This criteria itself is pretty bad. Okay, because even if you satisfy or do not satisfy, if the model itself may not even be causal model, a meaningful causal model in the first place. So all this thing is meaningless in a sense, right? So this is really saying that it's important to think clearly about causality rather than relying on the correlation argument to guide you for causal inference. Okay. Now I would say the other limitations are, for example, when we talk about causal inference as two-stage procedure, the first stage is identification. The second stage is estimation. The first stage can be non-parametric identification. Okay, it can be non-parametric. If we do backdoor criteria, it's non-parametric. If we do IV, it requires some parametric assumption. So the first stage is purely identification argument. It can be non-parametric. The second stage, we can do parametric or non-parametric estimation. They're separate. Okay, they're separate. We can have a non-parametric identification, and then we can have a parametric estimation, or we can have a non-parametric estimation as well, right? So this is pretty clear. However, the traditional econometric approach does not really distinguish between non-parametric and a parametric identification, because in the beginning it just gives you a parametric model, okay, just linear model. So it fails to do that. To give you a clear distinction between identification and estimation. Right? So identification in the traditional econometric approach refers to whether the parameters in the true model can be uniquely determined given infinity. So a true model is something like the linear model, okay, y equal to alpha 0. All right? But the true model already makes parametric assumptions on the underlying causal structure. When we talk about identification using the graph language, we don't make any parametric assumption. So that's a very big difference. Okay. All right. Okay. Now, finally, the traditional econometric approach does not give you an easy way of choosing control variables. So I think this one is pretty easy to understand. When you try to find what variables to control, right? How do you decide that? So if you know, traditionally, right? So the way you are taught is that there is a true model, which is y equal to beta 0 plus beta 1 x plus maybe e. So this is like some true model, and the true model, you know, x and e may be correlated. So in that case, you need to find some control variable to make them uncorrelated, conditional on that. But how do you choose that? How do you choose the control variable? And you have to think about all kind of things, right? But it doesn't give you a clear guidance. In using graph models, where you always start from a clear thinking about the underlying mechanism, it provides a very easy way to choose. Once you know x and a y, and you know there's a z here, there's a w here, all you need to do is to block all the backdoor path. So the backdoor criteria give you a very operational guide of how to choose the control variables, right? Which the traditional way doesn't give you, frankly. Because why? Because the traditional way doesn't require you to think very clearly about the underlying mechanism, right? Okay, so you're not required to say that. You're not required to specify that. Okay, and finally, it's often also not clear that we actually have a true model. Okay, now. Now, it's also often clear that we may not even have a so-called true model. Why? Here we assume there exists some kind of true model, like once you condition on Z and E, they're independent. But oftentimes they may not be such true model. What do I mean by that? Let's think about this graph, okay? So suppose let's take a look at this graph here. There's a W goes to C, C goes to X, X goes to Y. Okay? So in this case, first of all, let's go back to how many. I think I already asked you this question when I talked about causal inference. How many of you have heard the term selection on observable or no unmeasured confounding? Because in many books we say if there is selection on observable, then we just need to control for these variables, and then the causal effect is identified. Okay? Selection on observable means what? Means every confounder, all the confounders, all the things that leads to both x and y, all the confounders are observed. That means selection on observables. If there are confounders that are unobserved, it's called selection on unobservables. So in the econometrics literature, typically it is assumed that if we have selection on observables, meaning all the confounders are observed, then it's good. We just need to control them. If there's selection on unobservables, then we have to find some other ways. However, according to the backdoor criteria, we don't really need to observe. It's okay for us to have unobserved confounders. It's okay. Why? Take a look at this example. This W is a confounder because W leads to X and W leads to Y. So it's a common cause, it's a confounder. But even if W is unobserved, I'm perfectly fine here. Why? Because I just need to condition on C, right? Condition on C also block the backdoor path. So then I'm perfectly fine between X and Y. So in other words, even if we have unobserved confounder or selection on unobservables, we can still find out the cause. So this is not made very clear in the literature. Now let's take a look at this picture, right? So in this picture, well, also in this one, what are the variables I can condition on? I can condition on W, that give me the causal effect. I can condition on C, that give me the causal effect. I can condition on both, that give me the causal effect. So what is the true model? What is the true model? Is the true model W2 W plus E, or is it W2 C plus E, or is it W2 beta 2C plus beta 3 W plus E? What is the true model? It's not very clear at all. In fact, if I have C, right? Now, if I have this equation, then according to the backdoor criteria, this beta 1 will tell me the causal effect because I've already controlled for a variable that brought the backdoor path. But then in this case, this model is not even a causal model anymore because C is not a cause of Y. So when I add the C here, it's not really clear what this causal model is, what statistical model is. Everything is confusing, right? So that is, so the backdoor criteria give us clear guidance about what variable to control, and without the need of specifying a so-called true model. Because in this case, there's no true model. There's no unique true model. We can control for anything, C, Y, or CW, or both. So we have a number of so-called true model. Right? So the name true model doesn't make sense anymore, right? In this case. So finally, the backdoor criteria tells us one thing that's very clear, which is you can control for many things, but you should never control for something like E. Right? Because E already blocks the backdoor path. Right? If you control on E, what happens? You open the backdoor path. You open the back. So controlling for this E makes things worse, not make things better. This is something that the traditional way of thinking, which is making this uncorrelated with others, the traditional way would never be able to do. Okay, it's very hard for you to tell. Right? So that's why there's a lot of confusion in applied economic research about what variable to control. Many people say, I don't know what to control, I just add all the variables that are relevant into the model. And oftentimes when they do this, they're not very careful about whether they actually include a variable like this. It turns out you should never include a variable like this. And you should never include x goes to c, y goes to c. This kind of variable you should never include. And people often not very clear about that. But based on the graph, it gives you a clear guidance about how to choose those variables. Okay? All right. All right, that's it. Okay? So that's all I want to say about what I perceive as the limitation of the traditional model, econometric approach of causal inference. And today we're also running out of time. So next time we'll spend some time to talk about structural estimation, which I already talked about in my introduction, but